Hello, everybody. Thank you for opportunity to have a talk here. Uh, my talk is mostly a report about our discussion, which have been done on last few events, which was organized by this community, and I would like to thank not only for possibility to talking here, but also for the possibility to meet each other and discuss. I think it's important to have events like this. Our discussions is about how to simulate quantum computation with help of geometric algebras. Before, let me say a few words about the classical concept. You have to find many papers on it, and all of them are based on the following observation. Qubits can be realized as a Lie group SO2, which is isomorphic equivalent spin-free, which are in fact unit quaternions. And if we are looking for unit quaternions in geometric algebra settings, it's its nature to have even element in G3. If you do this in this way, you can see the direct implementation of so-called pole matrices in geometric algebra G3. It makes perfect sense, but if we want to work with n qubits, we have to do tensor product, and then we have to unify multiplication by complex unit in every slot. It means if we want to follow this approach, we have to live in factor space over this identity, which is called correlator. This system makes sense, it's completely correct, but if one want to simulate more qubit states in this geometric algebra, it becomes everything to be a bit of technical. But if there is a reason to use this system, it can be. I would like to show a few papers which we think are interesting, and if somebody is interested to do it by this way, it's easy to find some of this paper and use them. We think a bit of different. The quantum computation works over complex numbers naturally. So we ask the question how to choose the complex geometric or complex Clifford algebra to simulate quantum computation. What Clifford geometric algebra is? It's very easy. We have the same rules, we have the same multiplication table, just the coefficients are from complex number. So we can take any geometric algebra and define complex geometric algebra as a linear combination over this algebra such that coefficients are from complex numbers. In our specific case, we choose geometric algebra Gn. So we have n generators which are in the square identity. And then we have to simulate the multiplication by complex unit. The complex number are the same as even elements in G2. So we take an even elements in G2 because we add two new basis elements R1 and R2, and these two elements are in fact G2, and the even elements from this G2 are complex number for us. So we define quantum register algebra as a subalgebra in n+2 dimensional geometric algebra, such that all elements are in the square 1, and we take just a linear combination of the elements from Gn such that coefficients are from the C tilde. Now, if you look on it again, complex Clifford algebra can be seen and the direct product Gn plus Ign. In the same way, it can be seen as a linear combination of the element from the Gn with the coefficient from the C. Our quantum register algebra can be seen as linear combination of the element from the same geometric algebra with the coefficients from the C tilde. These two algebras are isomorphically equivalent as a real vector spaces, and they are isomorphically equivalent as a real geometric algebras. This year we have published paper where we solved how to use the complex Clifford algebra to simulate quantum computing. And according to this identification, we can translate all our thinking to the real world. And in the next slides, I will try to explain how to do it in detail. Before, let me mention one interesting fact. In the complex Clifford algebra, the signature doesn't matter because we can change the basis over Clifford numbers. So with help of imaginary unit, we can change the signature from plus to minus. So in complex Clifford algebra, the quadratic forms is described only by dimension. So the same thinking can be done over different real Clifford algebras. It's called a real form of the complex algebra, and maybe it would be interesting to do the same over so-called split real form. So instead of real geometric algebra Gn, use the real geometric algebra G and half and half. And maybe the computation will be more easy. Okay. Now, the goal is how to simulate direct formalism in our geometric algebra. To work with n-qubit space, we define quantum register algebra as complexification in our sense. So with help C tilde, geometric algebra with dimension 2n. And in this algebra, we choose so-called with bases. With bases is different base of the geometric algebra such that all elements of this basis is square 0, and we can directly write any element on n-qubit states from direct formalism to our algebra. So it's a bra vector is exactly this element, and ket vector is exactly this element. I will show next example 2 qubit states explicitly. Okay, the bit basis is not orthogonal. The original basis is always orthogonal, but bit basis is not. It's the same as in conformal geometric algebra. We can have orthogonal bases with n plus and n minus, or we can have bases with NO and NI to use the null element. This is in this case, we do some mix between the classical and with basis. Because the with basis is not orthogonal, we have to derive some extra identities which are needed for compute in it. But it's not very hard. We have two different cases of the element, without digger and with digger. And if you multiply two elements without digger, and these elements are different, it's anticommutative. If they are the same, it's zero. The same holds for the elements with digger. If they are different, it's anticommutative. And if they are the same, it's equal to zero. If one element is without and second is with, then it's anticommutative if they are different, but if they are same, this identity holds. So we have a set of identities which we have to derive because we changed the basis. The original basis was orthogonal and the with basis isn't. But the reason why we have changed it is this direct identification. So we found the basis, which is nature to use in quantum computing. But if we want to compute it in hands, we have to use these identities. For example, take 2-qubit states. If we have 2-qubit states, we have these 4 ket vectors, and we have these 4 bra vectors. During this identity I have mentioned, we just this 0 is d0, this 0 is d0. For example, this 0 is this, and this one is this. In the case of ket vectors, the first is on the second place, and the second is on the first place. You can see it here. If we have a bra vector, it's in opposite direction, and if we have a ket vector, is the direct direction. So this is the representation of the ket vectors. This is the representation of the bra vectors. If we would like to represent any gate, for example, swap gate, the gate can be realized as a matrix or in the direct formalism. The swap gate is just a matrix 0, 1, 1, 0, which is, this is the 0, this is the 1 on the first row, a second column. This is the 1 on the second row, a second column. No, this is 0, 1, 1, 0. First column, first row, second column, etc. And so it's very, very easy, any matrix to write in our formalism. You can see this 0, 0 ket vector is the I. For example, the 0, 1 ket vector is F2 degree E. F, yeah, it's exactly the same. And after this very easy computation, because we work in geometric algebra, it's distributive associative. So after this computation, the swap gate is exactly this element of our geometric algebra. On the other side, we can look how it works. these three identities I label 2, 3, and 4. And now I have swap gate, which is this element, and I have general 2 qubits, which is this element. This multiplication is just multiplication in our geometric algebra, so we can use distributivity and associativity. We will receive these 4 parts, and the cross is using the identity 4. This part vanished, and this underlying is using the identity 3. And after some computation in the hands, we will receive this. And finally, we will receive this element. And if you look on the input, and if you look on the output, you can see that 0, 0 is the same, 1, 1 is the same, and this 0, 1 and 1, 0 have been changed. So the multiplication by this element acts exactly as a swap gate if any qubit is represented by this element. Okay. This computation seems to be a bit of complicated because we have to use these identities, and these identities we have to use because our elements are written in with basis, but they are written in with basis because the with basis gives us direct identification of the Dirac formalism and our geometric algebra. And this slide is here just to show you that it works. If I need to check some computation, I can do it with if I use these identities. But generally, for computation, I use the computers. So we use Gallop, and in the Gallop, it's easy because we use bit basis. It's very easy to write any elements of quantum computing. So the swap gate is this element. General 2 qubit is this element, and this code just compute the result, and you can see the result. And what's the benefit of this approach? You can see this result, and this result is in the orthogonal basis from the start. So if you compute in some software, for example, in Gallop, the result will be always in the orthogonal basis. So the result will be in the most compact form. And we did some computation, and sometimes we have been surprised how short the result is. I think it's almost impossible to find the gate in orthogonal basis. But with the help of the with basis, it's easy to find, and with the help of Gallop, it's also easy to find the same in the basis, which is more optimal than with basis. Yes. And but if we in the end we would like to simulate any quantum circuit, so we have to deal with the serial gates and we have to deal with the parallel gates. In the case of serial gates, it's very easy. We have to just multiply these two elements, and the result will be the quantum circuit as a function. This example show us this is very easy example. We choose not gates and applied not gates 2 times, so we have to receive identity. And it's happened. If you multiply these 2 elements, the result after some computation in the geometric algebra will be I, which is identity. In the parallel gates, the situation is a bit of complicated. Why? If you do the same in the matrices, if the gate is matrix, to do serial gates means to multiply 2 matrices. But to do parallel gates, you have to do tensor product of these 2 matrices, and it depends about the order. If you take 2 matrices and do tensor product, you will use one first matrix as an element in the second. And if you do in opposite direction, the final matrix will be completely different. So if we do it in our algebra, we have to be careful about the sign. If you do parallel gates from 2 not gates, I have used the same gate for both, and the order doesn't make sense, and so all the signs will be the same. But if I use 2 different gates, it can happen that some signs change, but it's just a technicality. If I want to compute parallel gates from these 2 gates, I just find with help of with basis, do 2 elements of the algebra and then multiply them with respect to distributivity and associativity, and then I have to check sign of these elements with respect to some rules, which can be easily done automatically, and it can happen that some signs are changed, which happened 4 times. This final element represents the gate C0, the parallel connection C0 and not gates. And any quantum circuit can be rewritten in your algebra by this way. Any gates directly with the help of this identification, and any serial connection, just the multiplication, and any parallel connection with the multiplication, and plus with some sign discussion. And the same what I was talking about, in the complex board we published this year in quantum information processing, and some thinking how to use this approach in quantum game theory have been published in ICACGA. And what I was talking about, the quantum register algebra, this approach was published in pre-proceeding of this conference. And that's it. Thank you for your attention.
Okay, we have now a short time for a few questions. I'll just shortly ask, that's the implementation which is now in a Gallup calculator for Gallup quantum calculator. Is that correct? Is the implementation, the quantum register algebra is the one which is now used by quantum calculator, yeah, right. Are there some other questions?
Hello, Anthony Lazenby here. So in the parallel case, there's presumably a definite correct answer to that, and it's not a matter of discussion what the signs are. I didn't really follow why there wouldn't be a defined answer.
About the sign discussion in the parallel case, in fact, we do tensor product. So we can do tensor product, but we can use the distributivity and associativity. Then after this, we have this element. We have this element as a tensor product, and this tensor product is in fact over super algebra, not over algebra, and we have to discuss this sign before. It can be plus. This element has to be the same, but it can be plus or it can be minus, and it depends. It's something. It depends about the grades. but about the grades in which basis.
Okay, but the two gates taken together
Yes.
in parallel they must be equivalent to some operation which goes from the original algebra to itself, I would have thought. So I'm surprised you can't express it without a tensor product as a final answer.
No, the tensor product is a final answer, but we have to find the element from the geometric algebra,
Yeah.
which acts exactly as a tensor product.